Welcome back to linear algebra. Let's jump into Anki. Seven flashcards due. Here we go. How is the inverse of a product invertible of an invertible matrices? How is the inverse of a product of invertible matrices related to the inverse of the individual factors? The inverse of the product is equal to the inverse of the individual factors, but in reverse order. How many solutions does a homogeneous linear system with more unknowns than equations have? How many solutions? Homogeneous. More unknowns than equations can have infinitely many solutions. So you're going to have free variables. It is proved in the text that the inverse of an invertible matrix A is also invertible. How is A related to the inverse of, how is A related to the inverse of the inverse of A? They're the same thing. I feel like we did these yesterday. Why am I getting these again? If A is a square matrix and n is a non-negative integer, what does the symbol A to the power n denote? Non-negative. So if A is 0, it's going to denote the identity matrix. If A is not 0 and is a positive integer, then it's going to denote A times A times A n times. What is the difference between Gaussian elimination and Gauss-Jordan elimination? Gaussian elimination basically only does the forward method. Is that correct? Yeah. Gaussian elimination gets the square matrix into, not square matrix, Gaussian elimination gets the matrix into row echelon form, whereas Gauss-Jordan elimination gets it into reduced row echelon form. What condition must be satisfied for matrix A to have an inverse, and what is the inverse called in this case? A, B, C, D is a 2x2 square matrix. For it to have an inverse, you need to have A times D minus B times C to be not equal to 0. What is the inverse in this case? 1 over the determinant, aka AD minus BC, times a 2x2 matrix in which position row 1 column 1 is D, row 1 column 2 is negative B, row 2 column 1 is negative C, and row 2 column 2 is A. If A is an invertible matrix, how is the transpose of its inverse related to the inverse of the transpose of A? It's going to be like the transpose of the inverse is equal to the inverse of the transpose. I swear we did that yesterday. Maybe that was a new flashcard or something. Okay. Anyway. 64-day streak here. Wonky, that's cool. This is actually super cool. I didn't realize you can go into Anki and click on specific days with this plugin. Oh, wow. You can see what flashcards I was doing on those days. That's cool. Anyway, kind of just wasted some time. I'll add that back in. I'm going to grade the work I did yesterday and then go from there. We got both problems right from yesterday, so I'm going to continue working on this proof. All right, so I did tons of just like thinking and brainstorming, and eventually we got the proof starting here. I always do it very like language and thinking based, but essentially yesterday we identified that we need to show it's if and only if. So let's show the forward and you call it the converse. So show the forwards, or the, what do you call the original statement? Anyway, show the original statement and the forward and the inverse. No, not the inverse, the converse. So the positive and the converse. Show them that they're both true. So eventually you get to if A and B have the same reduced row echelon form, then we know that you can get both A and B from using only a sequence of elementary row operations on the reduced row echelon form. Right? We do know that. If we know this, well, how do we know that? Because to get A to reduce row echelon form, you need to use a sequence of elementary row operations. Same for B to reduce row echelon form. If we know this, then we know we can get A from B and B from A, because we can use the elementary row operations to go from B to the reduced row echelon form, which we already showed, and then from the reduced row echelon form back to A, and A to the reduced row echelon form to B. So we know they are row equivalent because we are only using elementary row operations. If A and B are row equivalent, then we can go from A to B and B to A using elementary row operations. We then can also go from A to B to the reduced row echelon form, and B to A to the reduced row echelon form. Since we start at A and get the reduced row echelon form, we know this is the only reduced row echelon form of A by definition of reduced row echelon form. Likewise, if we start from B, we know this is the only reduced row echelon form for B. Since we go from A to B to the reduced row echelon form, we know that A and B must have the same reduced row echelon form because each only has exactly one reduced row echelon form, and we only used elementary row operations to go from A to B. Therefore, if A and B are MXN matrices, then they are row equivalent if and only if you can derive A from B and B from A by only using elementary row operations. So that was a big one. It really started to come, like I could start to sense why it's true before I could show it completely, but I think that's pretty thorough. And then this true or false was like, if you've got two elementary matrices and you multiply them together, the product has to be an elementary matrix. Is that true or false? And it's false. And I just provided a counterexample. So that's it for today. I'll talk to you tomorrow. See ya.